I want to recreate one of the oldest experiments ever. Just a stick, a measuring tape, and your location. On June the 21st, 2025, the day of the summer solstice, many of all you subscribers from around the world stood outside, stuck a stick in the ground, and measured its shadow. I asked you to measure two simple things: the length of a vertical stick and the length of the shadow it casts at solar noon. I could then calculate the solar elevation angle using trigonometry. The exact number was 1014 separate results over 43 different countries. As you move away from that line, north or south, the solar elevation angle decreases in a predictable linear way. In fact, the formula for it is pretty simple. The solar elevation angle should be 90 minus brackets latitude minus 23.4 brackets. So this here is a graph of latitude versus solar elevation angle for everything south of 23.4 degrees north. Now here is the graph of latitude versus solar elevation angle for everything north of 23.4 degrees north. And here they are together, exactly what we would expect on a globe. Now let's look at what the flat Earth model predicts for latitude against solar elevation angle. Shadows at solar noon should vary only because of the distance to the sun, not the curvature of Earth. Crucially, the relationship between solar elevation angle and latitude on a flat Earth becomes non-linear and asymmetric. So if you plot latitude versus solar angle on a flat Earth, the curve bends the wrong way. Predicted angles stop matching reality. The graph I showed earlier with the results from the experiment supports what we see on the globe, not a flat one. But we aren't going to stop there. Let's look at shadow lengths too, because they don't behave linearly. The relationship between the sun's angle in the sky and the shadow it casts is not linear. It's based on the tangent function from trigonometry. As the sun drops lower in the sky, especially below 30 degrees latitude, the tangent changes dramatically. That makes shadows grow faster and faster the lower the sun gets. This should create a smooth but steepening line on a graph, not a straight line. And that's exactly what we see. Over 1,000 results of recording the shadow from a stick, and we have proved a curved surface to Earth. If the Earth were flat and the sun was hovering above a flat surface at a fixed height, shadow lengths should increase at a very steady linear rate. But we're not going to stop there either. Now, I took a few of these submissions and I used those to approximate the circumference of the Earth.
So I picked these three locations. Location 1 was in Finland. That had a solar elevation angle of 52.95 degrees. Poland, that had a solar elevation angle of 63.30 degrees. Greece, with a solar elevation angle of 75.12 degrees. Between all three locations, the difference in solar elevation angle was 22.17 degrees. So by adding the distances between these locations, we get a total distance between location 1 and 3 of 2,562.41 kilometers. That 22.17 degrees is the equivalent to the 2,562.41 kilometers. Therefore, 1 degree is 115.58 kilometers. Multiply that by 360 and we get an estimated globe circumference of 41,608.82 kilometers. An astonishing result for a stick and shadow experiment run by the public.
You did that with sticks and shadows. So what did we prove after all this? We showed that the solar elevation angle behaves exactly as it should on a globe. We saw the shadow length follow a curved pattern, not a straight line. And we used that data to estimate the size of our planet. And we did it all without launching a satellite or trusting any government agencies. To everyone who took part, thank you. The world is wonderfully, predictably, and mathematically spherical.